lesson. Today it is lecture 5 of the course of Maintenance Modeling and Analysis, and we will be talking about forecasting. My name is Marcia Baptista, I'm an assistant professor at TU Delft, and I hope you enjoy the ride. Last lecture we talked about repairable systems, and we talked about how we can model the failures of repairable systems using, for example, stochastic processes, namely the point process. We have seen that a point process can be represented in three ways, using global time, local time, and the counting variable. The counting variable is especially interesting because using the counting variable and using the mean, we can get the mean cumulative function. So if you have several instances of repairable systems, you can obtain instances of the counting variable, and with that you can get the expected cumulative function. After you obtain the mean cumulative function, you can get the intensity function, which you get by derivating the mean cumulative function. Okay? And then we talked about the increments, which are related to the counting variable, and we've seen the property of independence and stationarity. Importantly, we talked about how by looking at the intensity function, we can classify a system as a system of minimal repair, renewal, or imperfect repair. Going from the abstract to the concrete, we went from discussing point processes to talking about a specific type of point process, which is the Poisson processes. And we discussed within the Poisson process the homogeneous Poisson process and the non-homogeneous Poisson process. And this was all that we have talked about repairable systems. In this lecture, we will talk about forecasting. So we will talk about how to forecast the failures of repairable systems, for example, and other things, like, for example, forecasting spare part demand. Learning objectives for today. Today we will introduce the topic of forecasting, and because forecasting needs to forecast something, we will talk about time series, which are the thing that you want to forecast. We will introduce some basic concepts of time series and forecasting. We will talk about how, given a time series, we can decompose it into other time series, into its elementary time series. We will also talk about pre-processing techniques. And finally, we will talk about forecasting techniques. We will also talk about evaluation metrics to assess if you're doing a good forecasting or not. So starting by an introduction to forecasting. COVID-19 was an unfortunate incident, and one of the things that helped, or that they used to try to help minimize the problem, was forecasting. So when you had time series like the incident cases that you see here over time, or the incident hospitalizations over time, or the deaths, or the cumulative deaths, you can always forecast what's going to happen next based on what happened before. Okay? And you can see here several predictions that were made. So here it's a prediction in blue, another prediction here. And you can see that some predictions were right on spot, while others were completely off. Okay? So the message is in forecasting is important, but especially difficult. Over time in history, we have witnessed several bad predictions, and we in fact do bad predictions every day. But these predictions were exceptionally bad because, for instance, Henry Morton said that the light bulb was a conspicuous failure, or the associate of Edwin L. Drake said that drill for oil would never happen, or even flight by machines would never occur. And these predictions were very incorrect, as we know now, But at the time, it was very hard to know that these inventions, that these novelties would be successful, because everything that falls out of the expected behavior of the normal behavior is very hard to predict. But what can we forecast? Well, we can forecast different things, such as, for instance, the weather forecasts, which are becoming more and more precise over the years, the stock market, or even several things in maintenance. I will now give some examples not from maintenance, but from general real-world examples, which show the importance of forecasting and how we can do forecasting. So for example, here you have electricity consumption in the US, and you have here 3 time series. This time series of commercial demand, this time series of residential demand, and this time series of industrial demand. And you see here the historical records of the time series, and you can see here the time series forecast. So every time that you have a time series, the data that you have is the historical records, the past, and the things that you want to forecast, the things that you want to predict, are the forecasting window. Importantly, here you have the Google stock price, and you can also forecast stock prices. How do you do that? Well, if you have a stock price fluctuating, you see here the upward trend and the real data in black. The blue bounds are the confidence bounds, the uncertainty bounds, and then you obtain a forecast after some time. So here you want to make a prediction, and here this is your forecast for the future. And then you can compare your prediction with the actual stock price after some time. You also have, for instance, the Euro USD exchange forecast, and you can see that the euro is dropping in importance compared to the dollar. And then you also have the historical records and the forecasts. But what is easier to forecast? For example, if I give you 4 examples, the daily electricity demand, the Google stock price in tomorrow, or the Google stock price in 6 months, or the exchange rate of euros to dollars next week, what is easier to forecast? Well, there's one thing that we need to be aware, is that it is easier to forecast for tomorrow than to forecast in a week or in a year. The longer it is the forecast window, the harder it is to predict the fluctuations of the stock price, or the exchange rate, or the electricity demand. But it's also important to be aware that you need to have a good understanding of the factors that contribute to the stock price, or the electricity demand, or any time series fluctuations. So you need also lots of data, and the more predictable the time series, the better. But importantly and notably, the future should be somewhat similar to the past. You should be able to guarantee, or to be sure, that the future will resemble the past. If the future does not resemble the past, it's much more difficult to make a prediction about the future. I've been talking about time series, but what is a time series? Well, a time series is a set of observations, like this ones, that are ordered in time. So if I switch this one by this one, it doesn't make sense anymore, because this observation comes first, then this second one. Okay? And what is forecasting? Forecasting is estimating the future sequence of the observations through time. So I have here only one forecast, but I could have other forecasts, and they all consist of the technique of forecasting. Terminology-wise, well, it's important to know what you are forecasting, and what you are forecasting is a random variable y. And then you have the historical record of observations, so everything in red is your historical record. And then you have the forecast, the y of t plus 1. And if it has some variability, you call that the variability of y of t plus 1. A time series can be classified according to the domain and to the range, according to the domain and to the range. According to the domain, you can see if the time series is continuous or discrete. Okay? And according to the range, it could be continuous, assume values in any range, or only discrete values. I now give examples of time series in maintenance. So one example is, for instance, time between failure, in which you have the failures over time, and you have how much time has passed since the last failure. And you can try to set up or forecast a trend here. There's also another example of, for instance, sensors, which in this case we show a temperature of an equipment, and you can also try to forecast how it's going to behave in the future. We here have several sensors, and for each sensor we collected a time series. So we collected information over time for how much that sensor fluctuated and varied over time. And we can also try to predict what will happen next. Finally, we have spare part demand example. So here you have a chart that shows how much the spare parts fluctuated over the months. So you can try to identify seasonality effects here, because maybe in the summer you need more spare parts than in the winter, for example. And you can also try to predict these fluctuations. Another thing that is important and that connects to the previous lecture is trying to predict the number of failures of a repairable equipment. So if you have a repairable equipment, you can know that it had 5 failures in the fleet of equipment that you have in month 0. In month 1, it had other 5 failures, and so on. And you can also try to predict these variations. Now we will talk about how we can decompose a time series into its fundamental elements, and which elements are those. A time series can be decomposed into its 3 fundamental elements, which are the trend, the seasonality, and the noise. And what do each of these elements mean? So the trend indicates if the series has an upward or downward long-term trajectory. So in this case of this data here, we can see that there's an upward trend. Okay, but we can also see that there are some periodic fluctuations, and that we call the seasonality. We call the seasons. So the seasons in this case would be these ones. So every time that a cycle ends, it starts a new cycle that ends approximately here, and the series repeats itself. Okay? And we also can see some spikes over here that are completely random and inconsistent with the data, with the other data, and that we call the noise, because it's an inconsistent element. We also can call it reminder. So the noise captures the unpredictable variations in the data. When we want to decompose the time series, we can use this expression. So the time series, the y of t, it's going to be equal to a function that will decompose the time series into its 3 elements: the trend, the seasonality, and the reminder or the noise. Each of these elements are a time series. Okay? We can decompose the time series using additive or multiplicative decomposition according to the f function that we talked previously. So if the function is additive, we will add up the elements to obtain the original time series. If the time series is done with the multiplicative composition, we multiply the elements to obtain the time series. When should we decompose the time series in an additive or multiplicative way? Those two ways are different, and we must understand when to use one and when to use another. And it all depends on the seasonality that you see in the data. So, if you see something like this, it's more additive. If you see something more like this, it's more multiplicative that you should use. So in this case, the amplitude of the seasonality in the different cycles, it's always the same. While in this case, the amplitude is increasing with time, or it could be decreasing. But anyway, it's never constant. So if you connect the two lines, you get something like this, which should be more or less like a triangle. While here, if you connect the amplitudes, you get a rectangle. So let's see an example of a classical decomposition on a real-world example. And the data that we have is data of the number of passengers of an international airline from 1949 to 1960. This doesn't have to do with maintenance, but still it's important for us to understand the time series decomposition. The first thing that you want to do to apply a classical decomposition, either in multiplicative or additive decomposition, they're all the same in this step, is to compute the trend component. So you should compute the trend. The trend, as we said before, it's the upward or downward trajectory. And how do we compute it? Well, we compute it with the centered moving average smoothing. After you get the trend, you can apply a transformation to obtain the detrended series. So you're going to apply a transformation by subtracting the trend time series from the series. And then you get the detrended series. Okay? In the additive decomposition, you always subtract. This is different from the multiplicative decomposition, but we will see that in a minute. And then when you have the detrended series over time, you can partition it year by year and put it side by side. So you see here the year of 1949 or the year of 1960. And they all seem to follow the same pattern. So you can average this pattern and get the seasonality. How do I know that the period for the seasonality was 1 year? Well, you have to look at the series and try to guess this from observation. There's not much that I can say here, because it varies according to the type of data time series that you have. Once you have the expected seasonality component, then you can apply another transformation. So the thing that you want to do is to first shrink this one into this one. It's exactly the same. And then you repeat this pattern over time, how many years you have in your original data. So basically you repeat the seasonal element over time. And then you get the seasonality here. How do you do this in a multiplicative decomposition? Well, it's kind of the same idea, but instead of subtracting, you divide. So by dividing the series by the trend, you get the multiplicative detrended, which, as you can remember, it's quite different from the previous one. And then you obtain from the detrended series another new seasonality. Why is this different? You can see here the difference, for example. Why is the additive seasonality different from the multiplicative seasonality? Well, they are different because they were based on different detrended series. Putting back all of this together, let's see how well the additive competes with the multiplicative decomposition. So if I add the seasonality that I've got to the trend, the additive trend, and if I multiply the trend by the seasonality, who's going to win? Who's going to be closer to the real data? Well, the multiplicative wins because, as you can see in the real data, there's a triangle here. So the amplitude is growing over time. And then finally, if you want to get the third element, the element of noise, what you do is you get the series, you take the trend and the seasonality, and you obtain the remainder or the noise. Okay? While in the multiplicative, you have to apply this formula where you divide by the trend multiplied by the seasonality and you get a different noise. This noise is much more random than this one, meaning that the decomposition was actually better. Again. So, to summarize, we have 3 elements of a time series. 2 of them are consistent, and 1 of them is inconsistent. This means that they are quite unpredictable. These ones are more or less predictable, or it's easier to predict and to forecast, while the third one is much more difficult to predict. I talked about moving average smoothing, but I never entered into much detail, but I'm going to do it now. So the thing that you need to know is this formula here, which lets you calculate the smoothing at time t. So you are, for instance, here at time t, and you make a window of m around t. And with this window, you can calculate the average of all these elements that are within the window. And this gives you a value for the smoothing here. I'll try to give an example. So here you have an element, the t. T equals to 3 because you are here. And you want to calculate the moving average smoothing for t equals to 3 with an m of 5. Okay, so you're going to count 2, a k of 2 for each side of the window. Okay, how do we calculate this? Well, we calculate this as 1 plus 2 plus 3 plus 4 plus 5 divided by the number of elements or the window size, which is 5. And that gives me 3. But what if the m was 4? Will I consider this window, or should I consider this window? Okay, what should I do? Well, the thing is, you have to consider the 2 moving average. So you have to do the moving average here and the moving average here. And then you average the 2 of them. So the first moving average that I'm going to calculate is the moving average of 2.5. So the center will be here, and it's the yellow moving average. And I'm going to calculate this 1 plus 2 plus 3 plus 4 divided by 4. And then for the moving average of 3.5, 3.5 is here. So I'm going to calculate the moving average of 2 plus 3 plus 4 plus 5 divided by 4. And then I just add up the 2 factors and divide by 2. And I get again 3. The window size is very important because the larger the window, the smoother your trend in the end is going to be. So for example, if you use a simple moving average of window of size 2, you get this time series which has some fluctuations because it's considering a small window. But if the window has a size of 4, a bigger window, then in that case you can see that you have less fluctuations, because the more data points you consider in your calculations, the more cancellations are going to happen because of the fluctuations that will cancel out, and the smoother the result will be. So, message: the higher the window, the larger the window, the smoother the time series will be, resulting from the moving average. Okay, so a very cool next step is the pre-processing step, where we will we will give music to the time series. So let's see how. One of the things that you need to do to your time series to make sure that it's a good time series is to data clean. Is data cleaning. Meaning, if you have outliers of noise, you should get rid of it, or at least try to minimize its impact on the time series. So for instance, imagine that you have a time series like this one, and then you have all of a sudden a point here. Okay, instead of the point sitting right here, it sits right here. Okay, this is an outlier. It's clear to see because it deviates a lot from the normal distribution of the data. Okay, but noise are more tricky and intricate to guess, because usually there is a lot of noise. There is not just one point scattered somewhere very far away from the rest of the data. So the noise can be, a time series can be contaminated with noise, and you have to use other techniques to identify noise. One thing that you can do is that you can gather all your data points and understand which of those data points are outliers. How do you do that? Well, you can use the z-score. The z-score helps to understand if a data value, if a data point is greater than the mean of the rest of the data. Okay? And it tells you how many standard deviations away from the mean you are. Okay? You calculate it by calculating the mean of the data. You calculate the standard deviation, and then for each data point, you calculate the distance from that data point to this other component. According to the z-score, you can identify if the data point is an outlier or not. How? If the z-score is 0, then it's perfectly normal. And if the z-score is 2, then you can consider that maybe it's in the range of outliers, because it falls to this portion of the normal distribution. Okay? When you have a time series, sometimes it's important or relevant to transform it into another form that is easier to predict and to forecast. So for example, if you have a form like this, a shape like this of time series, maybe it's better to transform it into a linear trend. So if you have lots of points like this, maybe it's better to transform them into this shape. And what kind of transforms there are? There are many transformations, but I'm going to talk about the simpler ones. So I will talk about the power transform and the log transform. But be aware that if you transform y of t to w of t, then in the end, after you forecast, you have to reverse the transformation, because in the end what you want to know is these values and not these values. Okay? The power transform is based on the idea that it is usually easier to analyze linear transformations, linear time series. The power transform is based on the idea that it's usually easier to analyze the linear time series than the original time series very often. And the thing is, you apply the linear transformation where you have a time series of this form. Okay? So if you have here the p, what are you going to do? You're going to make a power of 1 over p. Okay? And then you get a linear trend. Quite easy, right? A simple example would be a data that would be scattered around this trend. And when you linearize, you get this kind of data. Okay, much easier to predict. If the data has an exponential format, maybe it's better to apply the log transform to linearize the data in the same way that we did previously. So if we have data like this, then maybe it's better to get it to a shape like this by using the forecasting techniques. Let's enter the world of forecasting. Let's see some methods that might be interesting to use in your time series forecasts. The first thing that I want to talk about is the moving average model. We have already talked about the moving average, but we talked about moving average smoothing. Now we will talk about moving average forecasting. It's quite different. If you check the previous formula, it's different from this one. In which when you are a T, you're not going to make this window like you did before. You're going to make this window. Okay? You're going to look at this M observations. So you always look to the past and not centered on the value that you are interested in, because you can only use information from the past to predict the future, and that is why this is forecasting and the other one is just smoothing. Okay, so importantly, the size of the window M determines the memory, how much memory you have, and how less reactive you are. So the smaller the window, the more reactive you are. The bigger the window, the more memory you have. Again, it's important to note that moving average forecast is different from centered moving average. So one looks into the past, another one looks into a window centered around the time point that you want to smooth. Okay, quite different. And here you see a difference. You see the smoothing moving average here and the forecasting moving average here. So they give different results for the real data here. Again, talking about the window size. So the window size is very important, and as I said, the bigger the window size, the more memory you have. So if you have a window size of 4, in this case, you're gonna try to forecast the next point. So let's do our first forecast. And we will do 4 plus 4 plus 5 plus 4, and we divide by 4 the number of elements or the window size, and we get 4.25. Okay? But what if the window was bigger? If the window was bigger, I wouldn't be so reactive to the late past elements. And what I would get would be a 3.5, because I would care about the 2. I would have a memory about the 2s that I have seen previously. So what is better, to have a bigger window size or a smaller window size? Well, it all depends on what you want. If you want to have more memory, if you want to be more reactive, and the window size can even change over time if you want. If you want to construct a customized moving average. But it's quite hard and quite difficult to figure out how to select the window size, even though there are methods for that. Properties of the moving average. A moving average cannot directly capture seasonality. It was not taught for that. But it is proper to use the moving average as every forecasting method to when the future is like the past. And of course, choosing a window size is quite difficult, but as I said, there are methods for that you can research if you are interested in that. A technique that I like really, really much is the weighted moving average, which is like the moving average, but this time with weights, so it's a little bit more complex. The formula is this one. And what you have is weights, and usually you assign a higher weight to the closest weight to the forecast, so to weight 6 in this example. And you may ask, okay, this is really cool, but how do I figure out which weights should I use? Well, the weights you should use can be according different arithmetical progressions, but they all have to add up to 1. So if you have these 3 weights in a window of size 3, when you add them up, they have to be equal to 1. This is what makes sense to make sure that you're giving fair weight to all elements. And for example, you could use this technique to calculate 3 weights, okay? So you set the window size as M and you calculate the weights accordingly, okay? And this gives 3 over 6, 2 over 6, and 1 over 6. So the weight of 3 that is closer to the forecast will have the bigger weight. This makes sense because usually the last observation is the most important. And what is so special about weights? They add up to 1. Okay, now a good one, single exponential smoothing. Single exponential smoothing uses both the previous observation and the previous forecast, so it accumulates observations in the form of a forecast. And it has this very cool alpha, this variable, this fixed variable that you use to acknowledge the weight of the last observation. Okay? So you depart from this formula and you easily get to this one. This one is usually what we use because you look at this and you see immediately what is the weight of the observation and what is the weight of the forecast. The larger the alpha, the more reactive you are to the data. When should you use the single exponential smoothing? Well, when you have data with only random variation, no trends or seasonality, and it's very useful for short-term forecasting. So here we have a table with the weights assigned to the observation so that we can see what happens. So if I choose the bigger alpha, then my last observation will have that weight. And if the alpha is smaller, then I have the last observation with the smaller weight. But then you have the second last observation given this weight, and in this case it's going to be a little bit higher because you're giving more weight here to the last observation. And this goes on like this. And what we can observe is that the weights evolve as like this. So if you are one observation behind, you are with 0.8. And then the second observation behind will be here. And then the third observation will be here. And over time, you are having an exponential decay. This is why we call single exponential smoothing, because the weights of the observations over time will decay exponentially. How can we choose alpha? Well, one way to choose alpha is by minimizing the sum of the squared errors. So imagine that you have actual values in the testing set, and then you have your forecasts, okay? So I forecasted something, and this is my predictions, and then I have the real data. I can calculate the distance from my real data to the forecasts, and I can see how much the error was. And then I do it again with another alpha, and then I can predict in a new time series what the forecast will be with more confidence. Okay, so now we have an example here of data, and then you have the smoothing moving average, the moving average, the single exponential smoothing with 0.2, and the single exponential smoothing with 0.4, giving more importance to the last observation than the others. It's hard to tell which of the methods are better than the others. Why? Because I don't have the real data here. Okay, if I had the real data here, I could calculate the errors and figure out what was the best forecast. Another method that I would like to talk to you is about Holt exponential smoothing, also called Holt double exponential smoothing. Why is it the double? Well, because he had this idea that if you divide the time series into trend and baseline, well, everything else, then you could forecast the two and then in the end bring them together. And this is why it's called double exponential, because the idea is like the single exponential smoothing, but over two time series. So here you have the forecast equation. So here you say that the next time series value, it's going to be an estimate of the level of the series, the baseline as I was talking about, plus the estimate of the trend. So you have here two components, the trend and the level, okay? And then you have two progressions of the baseline and the trend, and that are coordinated by two parameters, the alpha and the beta. This is very much like the the single exponential smoothing equations. And the idea is always that you have the level and the trend. Okay, so let's see an example. So here you have the data. And here you have in blue Holt's linear trend. And at some point it starts not smoothing, but forecasting. Okay, and it forecasts always with a linear trend. Okay, so now the fun part, getting ready to figure out if your forecasting was good or bad. Okay, so let's start. So when evaluating a forecasting method, we are interested in the errors, in the forecasting errors. And how do you calculate the error? Where if you have test data, which we usually don't represent in the charts, but they exist, then you just subtract the test data from the forecast, okay? And then you get the error. The error will be positive if the forecast is bigger than the actual value, and it will be negative if the actual value is bigger than the forecast. Okay, so one of the things that you can calculate, one of the most important metrics is the bias, and the bias is just the average error, okay? Why is this metric less good than the others? It's important because it shows the overall direction of the error, so you get to know if you're on average over predicting or under predicting. But because it cancels out negative and positive errors, there's no way of telling if your bias is indicating a good prediction or not. Example, if you have a bias of 0, but if the errors are canceling each other, so this cancels with this one, this cancels with this one, and this gets, so for instance, this would be -2, and this would be 2, this would be 3, this would be also 2, sorry, this will be also -2. When you add up all these values, you get a bias of 0. And you might think, okay, my model is really good, but maybe it's not because it has these errors, okay? And if the magnitude was even bigger, so 4, sorry, this one should be positive and this one should be negative. And if you have 4 and -4, then this all cancel each other also, and the errors are quite big. Right now we're not talking about just 2, but we're talking about 4 of magnitude of error, okay? So note on the bias metrics. A forecasting model can achieve low bias but still be not very good. But if it gives you a high bias, then you know that probably something isn't right. So it can tell you something. So it's also useful and important to measure this metric. And the signal of bias is important. That's the most important information that the bias gives us, is if we are under predicting or over predicting. Because of the problem of the bias, someone invented the mean absolute error. The mean absolute error has this formula, and it's similar to the bias formula, but this time you take the absolute value. Okay, so you take the absolute value of the error. And importantly, it now shows the magnitude of the overall error, but then we miss the direction. We miss if we are under forecasting or over forecasting. Okay, but importantly, it doesn't cancel out the positive and the negative errors, because all errors are first transformed into positive. The bad thing is that it's very sensitive to outliers. If you have very bad values, this will show greatly in the final score. The previous two measures were scale dependent, meaning that if you want to compare two use cases with completely different forecast measures, they will not work, because they will be on different worlds, different dimensions. It's not going to work. But the map tries to overcome that limitation. And when you use map, you have this formula here. And you divide the error by the absolute value of the actual value. Okay, and importantly, this is not scale dependent, it's scale independent. So you can have a forecasting for batteries and a forecasting for engines, and you still can compare, because the end is a percentage. Okay. Another metric that is very important, and it's also very used in machine learning, is the root mean squared error. The root mean squared error gives higher penalties for errors that are very large. Okay, so now we are ready to revisit the learning objectives. The learning objectives for today were, first, to talk about the relevance of forecasting analysis. We did that. We also talked about basic concepts of time series decomposition. So we talked about the additive and the multiplicative decomposition, so check. And we also talked about how to apply pre-processing techniques such as the power transform or the logarithm transform, so check. We also talked about a lot of forecasting techniques, from moving average to Holt's method, check. And then we talked about metrics and evaluation techniques, check. It's always good to talk about advanced materials, so you have very much online, a lot of things about forecasting, some tutorials that are important to go through if you want to start learning more about forecasting techniques are these ones. I didn't talk about autoregressive techniques, but they are also very interesting, and they can perform forecasting with quite successful results. If you want to see them, you have a tutorial here. And regarding evaluation methods, evaluating forecasting methods, it's a really cool paper to read. So thank you for watching, and see you next lesson.